So we're looking at trigonometric ratios. Trigonometric ratios in the Cartesian plane. And for this one, I'm going to make additional notes at the end of this document and go through it that way. And the point of this is to say, well, we've been looking at triangles all this time. Triangle, 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 triangle. But trigonometry is amazing in that we could transfer it and use it on the Cartesian plane. And let's see how that might work. Okay, so let's go down to the end of the document. There it is. Okay, so these are all updating, so it's in the same document you have access to. So far we've said we know how to work a triangle. We said if you've got a right angle triangle, there's our lovely right angle triangle with angle theta over here. Let's put it down the bottom left. So I'm going to say that angle over there is theta. Then what are trig ratios? Well, always know so, to. That's there just for reference all the time. Just so we got it there, so, to. And we went, okay, so what are our three trig ratios? We could have sine theta, and sine theta is opposite over hypotenuse. Right? We're getting quite comfortable with that. So the opposite, and I'm just going to write opposite in this triangle because I'm not going to look at this top angle. Just look at this angle and say, well, the opposite side would be this one, and the hypotenuse would be this one. Hypotenuse, the one on the other side of the right angle. I always say the other side instead of opposite the right angle, otherwise it feels confusing. Okay, so then we got cos theta, and cos theta, adjacent over hypotenuse. Cool. Adjacent over hypotenuse. Okay, the adjacent means next to, so it's this one here, adjacent. Cool. So we got our adjacent, opposite, and then our last trig ratio, tan theta. Well, we haven't looked at these two sides in some combination, because you see that the trig ratios, they just look at all the ways we could look at these three. And there are inverses, but we're not looking at those. So, tan. Toa, opposite over adjacent. Okay, so you think, well, this is stuff we've done. We're quite comfy with this, hopefully, by now. SOHCAHTOA, yeah. Or silly old tags and ends and all of that. Anyway, the point is we know our three trig ratios. Now, I'm going to say to you, all we have to do for the Cartesian plane, something really new to remember. What happens if we put that triangle on a Cartesian plane? So we put it exactly, I'm quite impressed with how my Cartesian plane came out. There it is. XY axes, and this point up here, we're going to call point P. And P has coordinates XY. We don't know what it is. In the examples we do, we're going to see it. We could say it's at 3, 4, it's at whatever. And the only additional thing that I'm going to add is to say, well, the hypotenuse we're going to call R. And the reason for that is it's a radius. We could move this thing around and make a circle, but we're going to call that R. Okay, now let's look at these three trig ratios in terms of X, Y, and R. So I'll ask you at times, what's sine theta in terms of opposite adjacent hypotenuse? It's opposite over hypotenuse. What's it in terms of X, Y, and R? So it's still a ratio or a fraction. The opposite. Now the opposite side relates to how high this is. So we know that must be this y value over here. How high is it? What's the y value? So the opposite is the y value. The hypotenuse, I said we're going to label R. So that's R. Now right angle triangles, planting a seed, Pythagoras, definitely going to come up. Cos theta. Cos theta is adjacent over hypotenuse. Adjacent, well, that relates to how far along the x-axis we've got. It's this x value. Can you imagine point P were 3 across? Then this distance would be 3. So it's 3 hypotenuse. No, it's not 3. Sorry, that was my example. It's the x value. And the hypotenuse is R. Okay, and tan theta, well, we've got opposite. Opposite, we said, was how high it is. So how high is this point? It's y. Adjacent, how far along has it gone? Well, it's x. So that's all that this is. These are three trig ratios, but now in terms of x, y, and r. And we can keep doing this and go further on. So if we drew our Cartesian plane a bit further along and we said, well, we've got our x, y, and we put point P over here. So point P is some point x, y. It would make an angle over here, theta, so it keeps going further on. Can you imagine that this thing was sitting on the x-axis and it's just gone further around? Okay, so that angle here is theta. So if we kind of drew a dotted line, that would be a right angle. Well, these same things apply. Sine, cos, and tan. Remember, these are of an angle, so they of theta. So this outside angle, sine theta. I always think it's worthwhile just going back to our first basic freestanding triangle and going, sine is opposite over hypotenuse. Okay, opposite. Opposite, when we had our picture here, opposite was to do with y. How high is it? It's opposite that angle, so it still remains as y. It doesn't suddenly change because it's outside of the triangle. It's still y, and it's still over r. Okay, cos theta, adjacent over hypotenuse. Okay, adjacent, if we imagine the triangle in the first quadrant, because that's the easiest, I think, then theta was there, adjacent was to do with the x. And so it's still x over r. So these three are going to stay exactly the same. Tan, opposite over adjacent. We might just have scribbled this diagram to go, okay, opposite over adjacent, that was y over x. After you use it for quite a while, you'll say, well, that's easy. I'll just remember sine theta is y over r, cos theta is x over r, tan theta is y over x. Okay, so those are our three, no matter where you are on the Cartesian plane. So if we said, well, let's imagine that we could draw our Cartesian plane again and again. I just don't want to draw on the same one because it's going to get a little bit messy. And say point P could have been down here, x, y, and it is a distance r away, and it's gone round by theta. Or point P could have been sitting down here in the fourth quadrant, and so new point, we consider it could have been sitting a distance r away from the origin, and it's gone round by theta. That's that big distance there. Okay, quite a lot going on here, right? But it all started from that same idea. We've got a right angle triangle, opposite adjacent hypotenuse, just that this point here is xy, so it's y up. This bit here was like y, and the adjacent was like x. Okay, and these same ratios are going to apply. Sine theta is y over r. Cos theta is x over r. Okay, so there are just one or two things left to consider here, and that is, when is it positive? So one thing. And what are these angles here? So let's first look at the angles. So we're going to have a very busy diagram here. It's going to contain everything we need. If this angle of this line was sitting right here, it would be at 0 degrees, right? It wouldn't have gone anywhere. So you can imagine it's sitting on the x-axis, that's 0. Then it keeps going around. Now it's on about P in our diagram there. Then it keeps going around and it gets up to 90 degrees. So if point P were up here, this would be 90 degrees. And so we'd keep going. So we're sitting at x, and we go round, 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 and then we keep going. And if it was sitting all the way along here, this would just form a straight line. So this is 180 degrees. And if you kept going, where are we going? That way, that way, that way, that way, round, further round, we get down to 270 degrees, and we get all the way back here, and this would be at 360 degrees. So in other words, theta here, we can see it must be somewhere between 90 degrees and 180. Look at that angle. 90 would be on the line, so it's between 90 and 180. Let's see what happens in the third quadrant. Theta, well, here it would be 0. Up here, that would be 90 degrees. In fact, it looks like that in your diagram, right? 90 degrees. Then if it kept going around, then it would be 180 degrees. This has gone further on, so that angle, can you imagine you measured it? I don't have a protractor on me, but if you measured this angle here, it would be 190, 200, 210, something like that. But it definitely isn't up to 270, because this angle here is 270, and if you had gone a full revolution, you would have gone 360. Now, as I said, we're easing and we're going to be doing a few exercise and examples on this, so it's quite a lot going on. Okay, the last bit is to look at when are these ratios positive and negative. So let's look in this first quadrant. In this first quadrant, is x positive or negative? If you've gone along, it must be positive over here. What about y? Is y positive or negative if your point's sitting up here? Must be positive because you've gone up. So therefore, and the radius is always positive. Must be a positive length. So what is y over r? Is it positive or negative in this first quadrant? Well, y is positive, r is positive, so it must be positive. Which means sine theta must be positive, because you must have gone a positive over a positive. Okay, everything's positive. X is positive as well, so x over r must be positive. So it must be, everything must be positive. Tan, what's y? Is it positive or negative? Positive. Is x positive or negative? Positive. These two numbers are positive, and the next three examples are going to show this with real numbers. So everything here is positive. In other words, they're all positive. What about in this quadrant over here? Is x positive or negative? Well, x is over here, so it's a negative value. What about y? Is y positive or is it negative? Well, it's positive. Okay, so sine theta in this quadrant, it's y over r. Is y positive or negative? Y we said was positive, and r is always positive, so sine theta in this quadrant must be positive. What about cos theta? X over r. Well, x is negative, and r is always positive, so this must be negative. So in the second quadrant, this was positive, this was negative. What about y over x? We've got a positive over a negative. This must be negative. So the only trig ratio that's positive in this quadrant is sine. So we're going to put an S in this quadrant to say that sine is the only positive one. And we're going to go around and keep doing this. So in the third quadrant's down here. We've got x and y. X over here, x is negative. Y is also negative. Everything's negative down here, except r is always positive. R is this distance. So, there we go. We've got them all in frame. We've got y over r. Y over r. Negative over positive must be a negative. What about cos? Cos is x over r. So we've got a negative over positive. This must be negative as well. Tan, y over x. What is the value of y? Positive or negative? Negative. And x is negative, so we're going to negative over a negative makes this a positive. In other words, tan is the only trig ratio that's positive in the third quadrant. So we're going to put a t here. Now, which ratio do you think is going to be the only positive one in this quadrant? And which one's feeling a bit left out? Cos, right? Nothing to say that it definitely must be cos, but it kind of feels right, and it is going to work out. So let's go for our fourth quadrant, and we normally use these capital Roman numerals. Doesn't matter if you write 1, 2, 3, 4. Okay, let's run through this. X, positive or negative here? Positive. Y, positive or negative? Negative. So, sine, y over r. Negative over r is positive, must be negative. This is sine. Cos and tan. Cos, x over r. Positive over positive is positive. Tan is y over x. Negative over positive is negative. So cos is the only positive one. So C. And the reason I'm just pointing that, we're going to re-go through it, is that if you wanted to know which trig ratios are positive where, they're all positive in this quadrant. only sine is positive here, only tan is positive, and only cos is positive. So this we call our cast diagram. And we're going to keep referring back to this. So for the next 2 or 3 lessons and videos, we're just going to be looking back at this and reinforcing why is this the case, why is this the case, why is this the case. Okay, so that's our trig on the Cartesian plane. It's looking like a lot right now. I can see, up, where's it up there? We've got all this triangle and this busy diagram over here. And it is quite busy. Starting point was just draw our triangle in the first quadrant so we can translate what we already know, SOHCAHTOA, into X, Y, and R. Going to make 3 separate videos on the 3 examples, so you can look at those separately. Got these down as notes, and let's go and look at some examples with real numbers, because it'll make a whole lot more sense when this is actually a 3 and a 4, and then we can work out this is 5 from Pythagoras, and we can see that they're positive. So let's go and do that.